Knowledge of biomechanics is important for understanding human movement, including those involved in sport and exercise, but also critical for those that are outside of the sport world. For instance, those who are just general public, rehabilitation, those who are looking to get back into shape, or those who are simply just trying to live a healthy lifestyle to extend life. In addition, there are special populations such as pregnancy, cancer, and also youth that having an enhanced knowledge base of how biomechanics influence and create an interactive movement will be able to carry out the design of a safe and effective resistance training program. So we'll be talking about skeletal musculature, body mechanics, movement patterns that can enhance and manifest human strength and power. Biomechanics can be defined as the application of mechanical principles to the study of biological systems. Breaking this down, bio meaning musculoskeletal system, and mechanics is the influence of force on the bodies. So an external force being applied to the skeletal muscle system. Okay? There are different ways to be able to apply both safe and effective rich training goals. So most of the skeletal muscle actually operates at a disadvantage due to the arrangement of how our bodies have the arrangement of our muscles and how those external forces are applied. So in the field of strength and conditioning, there are several mechanical concepts that we must understand to fully comprehend how most effectively and safely we can achieve these goals. Okay? If we think of lifting a barbell, some of those key mechanical concepts include force, distance, speed, inertia, mass, weight, velocity, acceleration, torque, power, and momentum, right? So many of these are derived from three basic variables. So all of those variables that I just listed off can be encompassed into three things: length, time, and mass. To illustrate many of these biomechanical principles, we can examine one of the most basic exercises, the bench press. In the process of lowering the bar to your chest, we think of straight up and down, but the actual pathway of a bench press is not straight up and down. So if you look in the image here, in the B portion of the image, it's a curve. Right? So in the process of lowering the bar to your chest and pushing it back up through space, it is a slightly curved path. Naturally, if you're telling the visual with long arms, you will be moving in a greater distance in comparison to someone with shorter extremities. So the distance is defined as the total path traveled by the bar in comparison to the displacement, which is defined as a straight line between where the movement started and where the movement ended. So again, distance, the length of path the body moves, and the linear distance is the meters, the angular distance is the degrees. So although there is a difference between the two terms, they are most often used interchangeably and to describe how far an object travels. Again, in a bench press example of a beginner versus someone who is an experienced lifter, A being a beginner, B being experienced, we can assume that the beginner may not take this linear line or this perfect curved line when we are completing a bench press. They push the bar in a greater distance and have more distance traveled because they are all over the place. Now, why? So we say, what are the differences between an experienced lifter and a novice lifter? Simply put, with distance or displacement, is that they travel further because they have the zigzag pattern as they move the weight from the beginning to the end phase, which from the top go through flexion of the elbow down to their chest and back up. It might not be this perfectly curved pathway. But why do they do this, right? Let's think back to exercise physiology now. The reason for this is that they're struggling to push the weight up and they don't take the weight in a direct line is because they are not experienced. They don't have the firing rate. They don't have the communication from the central to the peripheral nervous system. Now, over time, if we continue to have our client or our athlete do a bench press over and over, should we assume this shift from A to B taking place? Yes, right? With practice, we become more experienced in a pathway or a lift, and they become more efficient. The displacement or distance between starting and ending points becomes more efficient. Similarly, if the beginner lifter took longer to push the bar up, they would also have a lower bar velocity, often referred to as speed, which is defined as the displacement divided by time. So velocity, again, is also interchangeably with speed, but it's not exactly the same thing. So velocity, the rate of change over time. Velocity can be measured in any unit that divides a measure of distance by measure of time. So the most common unit to measure for velocity includes meters per second. Therefore, in order to calculate velocity, you must measure the distance the object moves and the time it took to cover that distance. For instance, a 100-meter race in 10 seconds. So the distance and time can be measured in several ways. These can include the use of tape measuring, timing gates, video equipment, or even electronic transducers. Okay, but why would we want to do this? We can find a number of different data points from collecting this information, and we can find the average of the 10 meters per second, split times, and it would help us better develop a program. Okay? Another illustration of velocity is the example of a sprinter finishing a 100-meter race in 10 seconds. So we talked briefly about this last time. But if a sprinter achieved an average run of 10 meters per second in 100 meters for over 10 meters per second, this gives a strength coach some information, but in order to tailor appropriate training sessions to improve the sprinter time, more information is needed. So if we know that a person ran 100 meters in 10 seconds, great. That's good information, but where are they weak? Where are they strong? We need to find more information. So if we are able to determine where their 10-meter split times are at, we can calculate velocity throughout that race. And would give us more information regarding the proportion of the race that needs most work. For instance, if there is a large drop in velocity towards the end of the race, the coach may need to design a program to work in more endurance, so the athlete can ensure that they are better able to maintain the velocity throughout the finish line. In retro to that, if someone is weak at the start, we have to work on the acceleration phase. So does it become increasingly important to examine not just velocity, but how velocity is changing over time? Okay? We have a real-world application, switching gears from running to lifting a little bit. One component of acceleration that is constantly acting on the human body is acceleration due to gravity. So, for instance, force equals mass times the acceleration of the dumbbell plus mass and the acceleration due to gravity, the 9.81. So with a concentric muscle action in the dumbbell curl, where we're going in an upward phase, gravity is a resistance force that results in a negative acceleration. In comparison, or in the opposite, with an eccentric muscle action to lower the dumbbell from the shoulder down back to the floor, eccentric muscle action, the force of gravity results in a positive acceleration. Acceleration is defined as the rate of change of velocity over time. So velocity and acceleration both refer to linear and angular motions or rotation. So we are going to discuss angular rotation or angular motion because we rotate about an axis. So everything we're talking about is linear so far, but we also have to remember that it's not linear motion. We are actually producing an angular rotation about an axis for a linear movement to take place, right? So distance between velocity, what's the difference between velocity and acceleration? So acceleration is the measure of how velocity changes over time, right? In a bench press example, acceleration of the bar is achieved through the application of force. So if we wanted to move into the force is the measure of newtons. In the US, we measure it in pounds. But if you see newtons, we're talking about strictly force. So again, acceleration is measuring how velocity changes over time, whereas velocity is meters per second. Okay? The amount of force being pulled or pushed upon an object can be calculated by multiplying mass and the object times its acceleration. Mass is the quantity of matter of an object. So force equals mass times acceleration. But weight is mass multiplied by the acceleration due to gravity. So if we take our mass on Earth versus the moon, it's going to differ. So mass is simply the mass of an object. Weight encompasses gravity at 9.81 meters per second on Earth. So for instance, if a person with a mass of 100 kilograms weighs 981 newtons, because we simply took 100 kilos, multiplied it by 9.81, that gives us 981 newtons. While on Earth, while in space, in a zero gravity environment, this person would be essentially weightless and would stand on the moon with a person to weigh only roughly 162 newtons because of a little bit of acceleration. Okay? So we have inertia, which is the resistance, Newton's first law, where we're talking about an object will stay in motion as long as it is not acted upon by an outside object. And we have Newton's second law, the law of acceleration, F equals ma, mass times acceleration. So force equals mass times acceleration. And Newton's third law, law of reaction. So if you jumped or pushed off the ground is going to push against you. Momentum is the quantity of motion that an object possesses. It's calculated by velocity times mass. An important point to remember is that in training, momentum and inertia patterns of a sport or activity should be mimicked during training. So we should not train muscle, but train motion. Okay? We should train the movements that are being done on the field, in the court, in the house, and train those to strengthen the movement for each person rather than the muscle itself. Not saying that training muscle is not important, but the greater transfer effect from the gym to the field or to real daily active living would be greater. Another thing to consider is the greater the momentum, the greater force needed to stop it. For instance, a football athlete running, they have a greater amount of force, so you'll need a greater amount of, they'll have a greater momentum, so they'll need a greater amount of force to stop and overcome their weight. So how do we implement this into a program? Increasing intensity during a workout. For instance, you can increase weight, reps, the workload. You can manipulate these in multiple different ways to enhance the force and enhance power and ultimately overcome momentum as needed. A couple of definitions. Work is force times distance, and power is the rate of doing work. So work divided by time. Power for me, in this class, I prefer to use the equation force times velocity. So power can also be calculated as force times velocity, which is speed strength. So for this class, we'll refer to power as force times velocity, and it'll make a little bit more sense as we move through this PowerPoint. Okay. Commonly used for slow moving exercises such as bench press, squat, deadlifts, is force. Okay, it can typically during these movements we produce approximately half the power of a faster Olympic lift, such as a clean or a snatch or a jerk. As can be seen in the formula, force times velocity, we want to be able to optimize both force and velocity, which equates to power. So the greatest amount of power output with large amounts of force to get moving is required, and the movements for these exercises are typically too slow for optimal power. So when we combine them, optimal power is calculated at 30%, meaning the greatest amount of weight lifted will be 30% of your 1RM at the fastest rate. So let me give you an example. If someone can lift 100 pounds one time, the fastest they can move is if we reduce that weight to 30 pounds. And then they can maximally move at 30 pounds with the greatest amount of velocity. Conversely, if they have a heavier load, they will not be able to accelerate at high speeds. So with lighter loads, they can accelerate with higher speeds, but do not include the ability to achieve the greatest amount of power production. So I'll show you a force velocity curve here in a little bit, and we'll talk more about that. So in a real world application, for instance, if there are two individuals who lifted the same amount of weight over the same distance, they are doing the same amount of work, yet if one of these individuals can produce the lift in a shorter period of time, they're moving faster. The velocity is increased. Therefore, the person is said to be more powerful. What's my point with force, velocity, and power is that most sports and even everyday living require power rather than force. So we can't just simply ignore the velocity component in training. We have to focus on both force and velocity and then combining the two. So we're going to be along this full spectrum of our force velocity curve to enhance overall power. Right? We know the obvious in football or in sports that power is required. But what about in everyday living? Why does grandma and grandpa need to include a power component within their training program? Well, think about them walking. If they're walking and then they trip, what do you do when you trip? You swing your leg fast. You produce a force, right? You're using the skeletal muscle to contract. So together, force and velocity, you're producing a power to swing your leg through and reestablish a base of support so you don't fall. That's why it's critical in not only just athletes, but everyday living, youth, special populations, to include a power component within your training programs. Now, they may not look identical where you're having your all your clients mimic an athletic program where they're just lifting weights with Olympic lifting, such as a clean, but power is going to look slightly different. They might be just simply hopping on one foot or a double pogo. There's a number of different ways that we can implement power rather than the traditional power we may be thinking of for athletes. Force of power applied is determined by a complex range of neural and mechanical interactions within a muscle, between muscle and tendons, and then between muscle and the skeleton. Okay? Angular motion, movements that take place about an axis or fulcrum, they're used interchangeably, axis and fulcrum. They occur in segments, so foot to lower leg to thigh, rotation about an axis, creating at the joints, the ankle, knee, hip, for instance. Okay? Torque, in order to lift a dumbbell, we need the bicep brachii muscle to produce work and have an upward rotation, a direction. So how much torque is produced depends on the amount of force being utilized and multiplied by the torque arm, which is also referred to as the force arm. Okay, so the torque arm is defined as the perpendicular distance between where the force is being applied and since the attachment of the bicep to the bone and the axis of rotation. So in this image, the lifting dumbbell through the concentric activity at the base requires a counterclockwise torque of the greater amount to them. So the clockwise torque being produced by the dumbbell. So that is the force, that torque arm of the bicep has to be greater than the weight of the dumbbell to produce the concentric elbow flexion. From the previous slide, rotary refers to an object resistance to being spun. So for instance, a person that will not be able to run nearly as fast as when they're able to flex their knees. So in this first picture, we're demonstrating how if someone were to run straight-legged versus someone bending at the knee, one will be able to run faster and more efficiently. So if you were not able to run nearly as fast when you're able to flex the knee during the swing phase of the running gait, while the legs themselves are not changing their mass as a hip flexor extends the outstretched leg with maintaining the mass of the lower leg and the foot relatively far from the hip, which is the acceleration creating a large amount of rotary inertia. So through this example, it demonstrates how mass bringing it closer to the axis or the axis of rotation promotes faster rotation. So when we bring the mass closer to the axis of rotation, we have a faster rotation. So think of a back flip. If a gymnast flips backwards and tucks into their body into a small little ball, they can rotate faster as opposed to rotating in a flat, straight line. So another good example of this is when an individual walking a tightrope. So these daredevils, often carry a long pole in their hand as they bend down from the weight attached to its end because they're adding more weight, so they're able to lower their mass and reduce their rotary inertia. Balance and stability is also a part of making sure you have a well-balanced, no pun intended, training program. So balance is the process of controlling body positions in either static or dynamic equilibrium, and stability is the case or difficulty with each equilibrium that can be distributed. So one way to increase an individual's stability is to increase their base of support. So the base of support is defined as two-dimensional area, which is formed by the support segments of the body. So if you stand up and both your feet are on the ground, this is the base of your support. So coaches often ask their players to spread their feet shoulder width apart, rendering them more stable. Versus if you were to stand on a single foot, you will have less stability. So increasing the base support enhances to stability because it increases the distance your line of gravity has to move before it ends up outside your base support and causing a loss of balance. So your line of gravity is a line, an imaginary line from your belly button straight down to the floor. So if everyone stands up, shoulder width apart, and you shift your belly over your toes, you are now reducing the stability of your body. Now, if you shift your line of gravity further past your toes, you will eventually lose balance and need to reestablish a new base of support, or you will topple over. Factors that contributing to stability is also the height of the center of mass, so the point at which the mass is evenly distributed throughout the body. So higher center of mass equates to a less stability. So location of center of mass is relative to the edges of the base of support. So closer to an edge has lower stability in that direction. Again, if you were to shift your weight to your toes, you're going to have less stability. So Olympic lifting requires not only athletes to lift the weight above their head, but also need to demonstrate control of the weight by balancing for 3 seconds. So the balance is difficult due to high center of gravity position, since it's not uncommon for these athletes to be lifting more than 2 times their own body of weight. So the center of mass is now being distributed upward, so they have to lower their body to balance this out. So a shorter lifter would have a stability advantage over someone who is much taller at the same small movements, when the load would be a greater destabilizing torque on the taller lifter. When standing on 1 foot, for instance, base of support becomes much smaller, and the center of gravity can fall outside of the base of support dimensions at a faster rate, causing us to become less stable. So by training in this very unstable position, one can further develop the body's sensory and muscular recruitment strategies needed from the central to peripheral to maintain balance. So it's still critical to train both bilaterally as well as unilaterally to enhance muscular recruitment, and use pieces of equipment frequently to be able to improve an overall stable environment and increase the ability to maintain stability in unstable surfaces. Because if you think back to the field, think back to the court, not every step you take will be stable. There might be sweat, there might be ditches, there might be bumps, there might be dirt patches. So this is all equating to unsurfaced or unstable surfaces. So we need to mimic those the best we can in the weight room to be able to overcome that. Length tension relationships. We have 2 to discuss: the active and the passive components. So the active component consists of actin and myosin, which are the active proteins within the skeletal muscle to produce force, and the passive components consisting of the tendon that attaches to muscle and bone, which the muscle belly shortens, pulls on the tendon, and in turn pulls on the bone, creating motion. So simply like a rubber band, it kind of goes around or goes with the motion. It creates an inverted U shape, which we have a peak and also has 2 ends. The peak of this curve is the maximal active tension or force that can be produced corresponding to the position where the muscle is in an optimal position, and it allows for the greatest amount of actin and myosin cross-bridge interaction. So at that top of the U, we have the greatest amount of actin and myosin cross-bridge interaction, creating the greatest amount of force. As the muscle is increasingly stretched beyond its length, so now we're going to the end of this inverted U, the cross bridges are either being torn apart, so there is less tension and force, or there is too much overlap of cross-bridge interaction and there is no longer able to produce a greater amount of force. For instance, put your arm down next to your hip and do a bicep curl. As we go through the concentric phase, we're increasing the number of cross bridges being formed. Now, if you're at that 90-degree marker where your elbow is at 90 degrees, you're at that optimal overlap. That optimal overlap in the max curve peak. Now, if we continue up, going through this upward phase of concentric and bringing your wrist to your shoulder, once your wrist gets to your shoulder, you have reached the point where your cross bridges have become overlapped so much that they can't produce any more force or tension. Now we have to go back through the eccentric phase. As you move through the eccentric phase, the cross bridges are being torn apart, so the amount of tension and force of the active component on the muscle decreases as the length of the muscle increases. So the image in the top right corner, increase the length, increasing the tension. So the total tension force achieved when the muscle is stretched beyond its resting length is the sum of both the active and passive components. So the purple is our inverted U. The elastic tension, which is the eccentric, plus the concentric gives us the orange, which is the total tension, is all what this graph is showing us. Although the amount of force of a muscle can produce is important, perhaps something more important in human movement is the velocity at which muscle can develop this force. Right? So positive power can be produced during concentric action, and the faster the velocity, the less force developed. Remember that 30%. The faster you move is great, but remember there is a trade-off. There is a reduction in the force that can be developed. So strength and power. When the muscle action is produced against a high load, force is high, velocity is low, and vice versa. If the load is light, then the velocity is high. Okay, so the strength and power is inversely, or strength and, rephrase this, force and velocity are inversely related, right? Strength and force are interchangeably being used in this context. Is one better than the other? No, we need to make sure we encompass all spectrums of this force velocity curve. So in this image, you see this red line on the right side of the graph. We have up at the top, we have force that curves down and to the right, and then down on the bottom right side is our velocity. So as force increases, velocity is low, and as velocity increases, force is low. So we are using, again, strength and power. They're used erroneously interchangeably. Strength, again, refers to the muscle ability to produce force in isometric or slow velocity, whereas power refers to the combination of force production and velocity, force times velocity, which is what this graph is showing us. It is critical to train both. For instance, that older client falling example we used previously, we must move quickly and adjust the position of their center of gravity to widen their base of support to avoid falling. So training at all velocities and all joint angle specifics to the sport and movement will result in the greatest carryover in performance from weight room to field. The force velocity curve, known as the strength curve, is again the combination and length of tension and the angle of pull resulting in the strength ability. So we have along both axes, we have the force and velocity. And along this curve, we have maximal strength all the way down to maximal velocity, illustrated here as speed. But know that we're talking about maximal force, maximal velocity, and then we have that power combination. Force times velocity gives us that power output, where you see power right in the middle, right there. So if you were to draw a line from 0 along the axes through power in a curved manner, that's where 30% would take place. So for more complex multi-joint movements such as bench press, all the muscles involved in the shoulder, horizontal adduction, and elbow extension combine to produce within the strength curve. Now that could be maximal strength or even high velocity. It depends on the load being lifted. So we have to talk about our athletic and ready position. Why is that the most common position, or known as ready position? It's because it's in resting length, which is known as that maximal cross-bridge interaction. It's at the peak of our inverted U, where we have the greatest amount of force, the greatest amount of velocity, and at that point, we have the greatest amount of power. The sticking region is known as the combination of strength curve with the line of resistance for a given movement, resulting in a varying degree of difficulty throughout a specific point or multiple points within that range of motion. Typically, this is where you get stuck and you can no longer push or produce enough force to overcome the resistance. For instance, if you're completing a squat exercise, you squat down, and as you return back to the starting position, you are producing force against the resistance on your back or on your shoulders, depending if you're doing a front or back squat. If you get stuck and no longer have momentum, this is termed sticking point or sticking region. This is the point in which the movement, that the lift, is most likely to fail. Now, if someone can't push through this sticking point, should they back off? It depends. Yes and no. It depends on the person. It depends on the goal. If you have an athlete that you can help through the sticking point, it may be beneficial to have them go through this sticking region within their training regimen. If it's someone who's freshly off of surgery, obviously this may not be the best route to take. So again, it depends. And yes, you can help someone through the sticking region and they still can reap a good amount of benefits from helping them through without failing at the given exercise. Joints and ankle muscular torque. So muscles pull on bone at a distance from the axis of rotation, which is our joint. And therefore, they produce a torque that attempts to produce angular motion of the bone to which they are attached. So the amount of torque that can be calculated by multiplying the force by the force arm distance. As a muscle causes movement on the bone, the length of the force arm will change. So there are changes in the amount of torque generated as the muscle moves the joint through its range of motion, meaning throughout the range of motion, there's going to be different amount of torques that will be needed provided to be able to move through that whole range of motion. Okay, so in a simple hinge joint like an elbow or a knee, the flexors, the bicep brachii and the hamstrings, are at a mechanical advantage at the joint angle of a 90 degrees, as the force arm is the longest in this position. As the joint angle increases or decreases, moving down or up, the force arm, which is the muscle, decreases in length, creating a loss of torque and the same muscular force. So this is exactly going hand in hand with our inverted U, our length force relationship. So the lever arrangements of the bone, muscle, and joints in the human body create simple machines called lever systems. So the musculoskeletal system is a lever system in which the muscle pulls on the bone that rotates about a joint, which is the axis or the, again, fulcrum. The trade-off of the distance and force is called the mechanical advantage. So humans usually work at a mechanical disadvantage in terms of force, but an advantage in terms of distance and moved. So we're talking about the velocity. So in the next couple of slides, we'll talk about the different classes of levers and which one human movement has a better or an advantage in comparison to the others. The lever type is determined primarily by which of the three components is located between the other two. That is, the first class lever has an axis in between the other two, while the second class lever has a resistance in the middle, and finally the third class has force in between the axis and resistance. So the distance between the axis and the force, which is the force arm, and the axis, and the resistance arm, help determine the types of movement that each lever system is best designed to perform. So those levers with a short resistance arm and a long force arm are said to have a mechanical advantage. For instance, if a 180-pound person wants to move a 900-pound rock, they could do this most effectively by getting a board and wedging it under the rock and then balancing the board on the object really close to the rock, creating the axis of rotation. So if the distance between the axis and the rock is 2 feet, it creates a greater amount of torque that must be overcome in order to move the rock. So the person would need to then jump on the board from a far distance to be able to help with the torque. So third class levers are the most common and designed for speed and a greater range of motion. The physiological cross-sectional area, so the PCSA, is simply the measure of how many muscle sarcomeres that are arranged in a parallel in that muscle. So, in simply put, the measure of how many muscle or sarcomeres we have, the greater or bigger the muscle, in theory, the more force we have when compared to a smaller muscle. So we're able to produce the maximum amount of force for that specific muscle. For instance, the gluteus maximus. It's one of the largest muscles that we have. However, the downfall to this, even though we know the gluteus maximus can produce a great amount of force, it can sometimes not correctly fire. So a large muscle that does not fire efficiently or effectively will then require smaller muscles to compensate for when it doesn't work efficiently. So it's important to train appropriately, as extreme common pathologies such as a low back pain has been associated with loss of neural drive to this muscle, to the gluteus maximus, which is termed gluteal amnesia. So the point of this slide is, even though we have large muscles, it doesn't necessarily mean it's going to always fire correctly. So we still need to train it efficiently, and we can't forget about it. Even though we have this large muscle in the back, in our posterior chain, a lot of the time people forget to train posteriorly. We just want to train the anterior side. We always need to make sure to have an anterior and posterior exercise to ensure balance of our skeletal structure. So if we do a bench press, which is a push, we need to make sure that we're doing a pull in the back or something in the posterior side. For instance, a good example block would be if you were to do a bench press and then pair it with an RDL. So that is an upper body push paired with a lower body pull. And that way you're balanced on both sides. And that way you can switch it up the next day. A lower body push with an upper body pull. An example of that would be a squat with a pull-up. That way now we are completely balanced and we have targeted all of the greater muscle groups, but also training for movement, not necessarily just the muscle itself. The stretch shortening cycle. Most human movements begin with the motion in the opposite direction to the intended movement, such as a vertical jump. This involves the initial flexion of the hip, knees, and ankles used to accelerate the center of gravity downward initially. This creates an eccentric stretch of the hip and knee extensors and the ankle plantar flexors. That's quickly turned into a concentric action of the same muscles to produce an upward motion in the center of gravity, resulting in a jump. This, in short, is known as a stretch shortening cycle. The definition of the stretch shortening cycle is an eccentric muscle action immediately followed by a concentric muscle action. Now that word immediately is critical. If the immediate wasn't there, this would not be a stretch shortening cycle. For instance, pull a rubber band. You pull it back, you stretch it, and immediately let it go. And then do that again. But hold the rubber band now. We're sitting in the lengthening phase of the rubber band. We're waiting. What's happening to the rubber band as we're stretching it out? The elasticity is decreasing. So when we finally let it go, will it go as far as the initial rubber band? No. We've lost that eccentric or elasticity that was being built up. So we have to have an immediate eccentric to concentric muscle action. With the stretch shortening cycle, we have to talk about the muscle spindles. So the muscle spindles, like we mentioned, are stretching like a rubber band. We go through an eccentric, immediately followed by a concentric phase. But how? Why is our body functioning this way? It's due to the muscle spindles. So the muscle spindles, they lengthen, which activates the spindle, and it detects a change in length. It's detecting not only the change in length, but the rate at which the length is changing. So when we first detect this change, the sensory nerves sends an action potential to the spinal cord. The spinal cord assesses this information and sends another action potential through the alpha motor neuron, which is known as the monosynaptic stretch reflex, signaling the muscle to contract. So it's this loop process because we want it so fast that it only gets sent to the spinal cord initially, and eventually it'll go to the brain, but we don't want the message being sent from our quadricep all the way to the brain and all the way back down. It'll take too long. So we take a loop from our muscle to the spinal cord and back to our muscle to have this feedback loop occur for a rapid power response. There are a number of different ways that you can improve resistance training, from free weights to pulleys to hydraulic resistance to elastic resistance. And it should be clear that there is no single form that is the best. There should be used in the most efficient way, but you should have a basic knowledge of all forms of resistance and how they can be combined and altered to achieve the stimulus to meet each goal of your training programs for all your clients and athletes. As with any physical activity, there is a degree of risk of injury with resistance training. However, sometimes the risk involved are generally low in comparison to other sports. For instance, the rate of injury for team sports are going to be the highest, whereas injury for such as weightlifting is relatively low risk of injury, and it is desirable to minimize the likelihood of injury through prudent risk management. Some major points to make for our skeletal structure. For our back, for instance, when we are in a standing position, any force that we are exerting with the upper body, it must be transmitted through the back to the legs and then to the ground. So in addition, the back muscles act at a greater mechanical disadvantage and must generate forces much greater than the weight of an object lifted. So for instance, if it is for these reasons, the back is particularly vulnerable to injury. It should be noted, though, that a spinal internal load are quite variable with varying postures during the lift. So for instance, during a deep squat, this isn't necessarily a position with loads that are not necessarily associated with back injury. So squatting at different depths won't lead to back injury if the exercise is done appropriately. For the shoulder, it is particularly prone to injury during resistance training due to its ball and socket joint. The shoulder joint has the greatest range of motion of all joints in the body. So ball and socket has 3 or 6 degree, however you were taught from undergrad. And there's a 3 or 6 degree range of motion, which the shoulder has. But the joint's excessive mobility contributes to its vulnerability, as it does the proximity of bone, muscle, tendons, and ligaments. So high forces that are generated during resistance training can result in tearing of the ligaments, the muscle, or the tendon. So to be able to avoid this and to adapt to the stresses that are placed on the shoulder, it is particularly important to warm up with relatively light weight and to follow a program that exercises the shoulder in a balanced way. So in a nutshell, we need to make sure that we are utilizing an appropriate general to specific warm-up for the shoulder when we are going to plan on utilizing the shoulder to produce high forces for either strength or for velocity, force or velocity. The knee is also prone to injury because of its location between 2 long levers, the upper and lower leg. So the flexion and extension about the knee occur almost exclusively in the sagittal plane, such as a squat. So the patella's main function is to hold the quadricep tendon away from the knee axis of rotation, thereby increasing the moment arm of the quadricep group and its mechanical advantage. If inappropriate load or volume is provided, relative high forces encountered by the patella tendon during resistance training can lead to tendinitis, which is characterized by the tenderness and swelling. But there is no inherent risk of tendinitis with performing these exercises. It's simply when it's done with too much volume or intensity without appropriate progression, which we all know is critical when designing a training program. There is some research, but very little research, on the efficacy of knee wraps. There's been detrimental side effects that have been reported, yet include skin damage and also injury to the patella by wearing down or of this posterior surface of the patella. So heavy wraps around the knee don't really help outside of the notion that they stabilize the knee for psychological effects. There is not a lot of research supporting the use of knee wraps to enhance performance or recovery. And then lastly, we have the elbows and wrists. The primary concern with the elbow and wrist injury involve overhead lifts. So the risk of overhead lifting is quite small in comparison to sources of injury of other joints, but they are particular when throwing events or tennis serves or overuse injuries. So other examples of possible injuries are elbow dislocations, sometimes observed in gymnastics, or overuse injuries such as traction and observed in diving, wrestling, or even hockey. So it is hoped that the biomechanical principles discussed and applied in an appropriate design will enhance not only just performance, but hopefully prevent any sort of injury when it comes to the skeletal muscle system.